Okay, we'll go ahead and get started here in a minute. Welcome everyone to the Center for Quantum Networks Winter School on Quantum Networks. Today we have Professor Ito Wax doing a course on quantum memories for quantum networks. And just a couple of things. The chat is disabled, so if you have any questions, please put those in the Q&A. And then at the end of all of the courses, we will have recordings posted on the CQN's YouTube channel, and we'll get all of that information sent out as things wrap up in the winter school. But otherwise, you guys are all set to start your course.
Great. Thank you very much. I want to thank everybody for joining us for this tutorial on quantum memories for quantum networks. My name is Ito Wax. I'm a professor at the University of Maryland, and this tutorial will be co-taught with two of my colleagues, Chaohan Q and Michael Kwan, who have been very kind to lend their expertise on various quantum memories and quantum networks. That's So this is the tutorial structure. The tutorial is going to be in three parts. I will teach the first part, which will be an overview of memory-enhanced quantum networks and the role of memories in quantum networks, why you want memories in quantum networks, what they do, what advantages they deliver. And then I'll also go through an overview of the state-of-the-art network demonstrations that currently exist. After that, in part two, Dr. Q will give a tutorial on solid state quantum memories for quantum networks. So he's going to focus on solid state implementations of quantum memories and how they can be used in a quantum network to achieve advantages. And then in the third part, Michael Kwan will discuss atomic memories for quantum networks, focusing on trapped ions, neutral, and hardware, the network hardware required to interconnect them. So let me first begin by the way, are you flipping my slides or am I doing it?
You're doing it.
I'm doing it. Okay, interesting. It might be on a timer, so let's see if it flips on me. So I want to begin by distinguishing quantum communication versus quantum memory-enhanced quantum networks because it's an important distinction that sometimes get confused and it's a little complicated by the fact that quantum networks can implement quantum communication, but there are some important differences. So in quantum communication, the most common context you come to is quantum key distribution, where the goal is to just exchange a random classical key between two parties for secure communication. The key point about quantum key distribution is that the goal here is to distribute random classical bits. The quantum communication itself is used to achieve security and detect eavesdropping, but the overall data being exchanged is generally or almost always classical set of zeros and ones that form the cryptogram. And because of that, many protocols for quantum key distribution can be used. You can work with just classical light sources and detectors. They don't need quantum numbers. In a quantum network, our goal is more general. We're trying to actually transmit quantum bits, qubits, over long distances and preserve their coherence. So our information is quantum fundamentally. And because of that, quantum networking is more difficult because not only do we need to exchange random strings of zeros and ones, we actually have to deterministically transfer quantum bits and preserve their phase coherence. And we also have to distribute that coherence over multiple nodes that can be distributed by hundreds of kilometers. So in the quantum network can, of course, be used for quantum key distribution, but not all quantum communication systems can actually implement what a real quantum network does, which is transmitting qubits over long distances. So one way that a quantum network can distribute qubits is simply by direct transmission. For example, you take a photon that has a qubit encoded in it and you try to send it over an optical fiber to an adjacent node, but that runs into inherent fundamental limits. In all long-distance quantum networks, loss can be quite substantial. And loss creates asynchronous photon arrival. So it means that the arrival times of different bits is no longer deterministic. it may arrive at different times, and that's problematic, particularly when you're trying to do quantum processing, where you collect information from different nodes. But more importantly, loss generates faults. When you lose a photon into the network, out of the network, that is a source of leakage of rich path information into the environment. And that fundamentally means that there's decoherence. And so in order to prevent this decoherence from killing any kind of advanced quantum information protocols that you might want to run, direct transmission requires very low loss rates, less than 0.1 dB. And so over any kind of reasonable length fibers, you're simply not going to be able to do any sophisticated quantum networking just because of standard fiber loss. So quantum memories are essential for scalable quantum networks because fundamentally they enable a way to overcome loss in probabilistic operations. They also enable error correction for high fidelity qubit transfer. So not only can we overcome losses, but we can overcome all of the other faults in the network, like coupling, phase randomization due to the environment, and other decoherence mechanisms. These can all be incorporated into a quantum network to ensure high fidelity transmission of quantum bits. Uh, Quantum networks also synchronize quantum operations across different nodes. We're going to see that in a very important example when we talk about quantum repeater networks. The ability of networks to synchronize probabilistic events allows them to do things that allows them to have important advantages, like, for example, overcoming channel loss. Finally, if you can truly transmit quantum bits and quantum information over a network, then that opens up the possibility to implement fully quantum multi-node network protocols like anonymous quantum communication, distributed sensing, and distributed quantum computing. And these very advanced protocols go well beyond just interchanging single qubits. They allow us to actually build distributed large-scale quantum computers that can do things beyond what can be done with just a single local processor. So these are kind of the important things that a quantum network can do. And in this class, I'm going to touch on all of those things. Here's the outline. I'll begin by discussing memory-assisted quantum communication and why memory is important for transmitting quantum information. I'll discuss quantum repeaters and long-distance connectivity and why how quantum repeaters use memory to overcome loss. I'll then discuss more advanced quantum networking protocols which pave a vision for an even more interesting set of quantum advantages that you can achieve when the entire network becomes quantum. I'll touch on the performance requirements for quantum memories, what they need in order to actually implement a useful quantum network, and then I'll conclude with examples of current state-of-the-art quantum networks and how far we've gone and where we need to go in order to get to where we actually want to be in the long run. So that's the brief outline. So let me begin by talking about memory-assisted entanglement distribution. So in a quantum network, the way that information is transmitted is not through direct transmission. It's usually done through a process called quantum teleportation. In quantum teleportation, we start between two nodes of the network that want to communicate. For example, we can call those nodes Alice and Bob. And those nodes exchange an entangled pair of qubits. So qubit pair that's in this entangled state. And I'll talk a little bit later about how we establish this state, but the ability to exchange entanglement is crucial to the operation of the quantum network. And in particular, it's the important ingredient for enabling a clear quantum channel between the two nodes. So let's assume Alice wants to transmit qubit 1 to Bob, and Alice and Bob have already, ahead of time, exchanged a pair of entangled qubits, qubit 2 and 3. The way that they will do it is they'll use these entangled qubits to teleport qubit 1 directly to Bob without exchanging any additional quantum signal. How is this done? Well, Alice is going to take her entangled qubit, qubit 2, and the qubit that she wants to transmit to Bob, and she will perform what's known as a Bell basis measurement. So in a Bell basis measurement, you measure these qubits in these four Bell states. These are the maximally entangled states of a two-qubit system. And basically, the Bell basis measurement has four possible outcomes. It has psi plus, psi minus, phi plus, and phi minus. This is a complete measurement basis. So when you perform a Bell basis measurement on a qubit, you will always get one of these four possibilities. And it is performed on the first two qubits of the total state of the system, which comprises the qubit that Alice wants to transmit to Bob, plus the entangled pair of qubits that are the resource for the quantum communication. After the Bell measurement, what you end up with on Alice's side is that qubit 1 and qubit 2 become entangled in one of these four possible entangled states, depending on the measurement result. So if we measured psi plus, Alice's qubits 1 and 2 are now in the state psi plus and are no longer entangled with Bob. Bob's state has actually been turned into a different qubit. It is one of these four possibilities, which is contingent on which measurement which measurement result the Bell basis measurement yielded. And the nice thing about these four possible states is that each one of them can be converted into the desired qubit either through a bit flip, a phase flip, or a combination of both. And we know whether you should do a bit flip, phase flip, both or neither, based on which state you got. For example, if you got phi, if Alice got phi plus, she knows Bob shouldn't do anything because he's already got the right state. Whereas if she's got psi plus, she knows that Bob needs to flip 0 to 1 and 1 to 0. And so based on her measurement, she can simply transmit over a classical channel to Bob whether he should do a bit flip, a phase flip, neither or both. And that immediately places Bob's qubit in the desired state. Notice what happened here. What we've succeeded in doing is teleporting Alice's state to Bob without having to send any quantum transmission. The only thing we had to send was a classical bit of data to tell Bob whether he should flip the bit or flip the phase. This information does not yield any, it carries no information about the actual state of the bit. It just tells Bob whether he should transform his bit or not. And so what teleportation allows us to do is to transmit a qubit from Alice to Bob using only classical data and shared entanglement. Once that's done, it's as if Alice and Bob's labs are automatically directly connected by a quantum channel mediated through this teleportation. Now, there's an important caveat. This does not allow faster than light communication. Alice does have to transmit classical information to Bob in order to construct his state correctly. She has to transmit to him whether he needs to do a bit flip or a phase flip. And this does take a certain amount of time, which is limited by the speed of light. So teleportation does not allow you to instantaneously transmit qubits. But what it allows you to do is transmit a qubit using only classical signals and shared entanglement, rather than directly transmitting the signal over the network. And as I'll show, that capability is essential for establishing many of the benefits that a quantum network can deliver. So before we talk about how entanglement is so important in a quantum network, let's talk about how one actually establishes this entanglement. And so the way that you actually create entanglement between two parties is you use photons. Photons really the unique carriers of quantum information over long distance. Anytime you want to transmit information, you have to, usually photons are your only choice. And so the way it works is as following. In each side, a node of the network will create entanglement between the qubit and a photon. Here's an example of an entangled state. This is a state where the qubit is in state 0 and the photon is in the horizontally polarized state, or the qubit is in state 1 and the photon is in the vertically polarized state. So the qubit state and the photon polarization are now in an entangled state, similar to the entanglement state that I discussed in the previous slide. The same thing will happen on the other node of the network. They will establish their own entanglement between their qubit and a different photon. These photons then propagate to a central station that performs something known as a photonic Bell measurement, which is basically a Bell measurement, just like the one I described earlier, but it's done on photons. Once the Bell measurement is performed, and classical communication is returned back to the original stations that reveals the state of the result of the Bell measurement, the states of the states of the two nodes become entangled. They become this maximally entangled state that I showed you earlier, which is the one we need in order to achieve quantum communication and quantum teleportation. And so the idea here is each qubit becomes entangled with a photon. The photons propagate to a central station where they are measured in order to swap the entanglement from the photons to the individual qubits, creating a photonic interconnect that entangles remote qubits over long distances. Now, I should point out that now you may be concerned here that these channels are lossy, and why isn't that a problem? Because it was a problem for direct transmission. And the answer is it is a problem because when the photons don't get to this photonic Bell measurement, they don't yield a proper result and we fail to distribute entanglement. But the important point here, which will be more clear when I give you concrete examples, is we can keep trying this over and over and over again until we succeed. And then once we succeed, that entanglement between qubit 1 and qubit 2 is stored permanently, or not permanent, for a long time because they're good memories. And by storing that entanglement, we can use it as a resource later when we want to do quantum communication. So think of this as a resource of entanglement that is being constantly generated over time and sitting in the background for you to use until you want to go do your quantum teleportation, and then you go grab one of these things and use it. So because of that ability of memories to store entanglement over a long time, this is where we get that benefit. Again, that'll become more clear when I describe things like repeater networks, where this will be really, really easy to see. But before I jump into that, let me talk a little bit more about how a photonic Bell measurement is actually made, because it really is important in order to understand what we need from a quantum memory. So a full Bell measurement is actually difficult to do. It requires things like single photon nonlinearity, which is not something that's readily available. But it turns out there are ways to implement the Bell measurement with a little bit of a cost, but at the price of a little bit of cost, we get tremendous simplicity. And this method uses only linear optics, and it uses an effect called the Hong-Mandel effect, or two-photon interference. Suppose we take two identical photons, same frequency, same pulse shape, indistinguishable particles, and we collide them on a beam splitter. When we do that, the photons will exhibit something called Hong-Mandel interference. In other words, the component where both photons exit out the same side constructively interferes, whereas the component where they both exit out different ports, whereas one photon goes to this detector and another one goes to this detector, that destructively interferes perfectly, resulting in zero probability that both detectors click at the same time. This only happens if the photons are 100% indistinguishable, which means that they have the same wavelength, the same identical pulse shape, the same polarization, the same everything. If they're identical, they will exhibit this Hong-Mandel interference, and that will prevent these detectors from simultaneously clicking. Why is that useful? Consider the spin-photon entangled, the qubit photon entangled states that I talked about in the previous slide. So if I send this state the photon associated with this state to one port of the beam splitter, and a photon associated to this from this state to the other part of the beam splitter, it turns out that when the polarizations are the same, you will never get a simultaneous click because of Hong-Rumental interference. But if the polarizations are different, in other words, if this polarization was V and this polarization was H, then you will get potentially some simultaneous click. And in fact, it turns out that if the photons are in the symmetric triplet Bell states, these three Bell states, they will never create a simultaneous click. But if they're in the antisymmetric Bell state, this one, they will, with 100% probability, create one click on this detector and one click on this detector, assuming they made it to the detector. And so by looking at the times when both detectors click simultaneously, we create a heralded entanglement where both photons, where a simultaneous click heralds the state of the two photons to be in this Bell state and therefore implements a Bell measurement. Were there any polling questions that we should have popped up yet? We may have lost our moderator.
Sorry about that. The first question was quantum networks are essential because
So are you gonna put, did you put them up
no, I didn't. So I
okay.
was, yeah.
Why don't we take a stop here and because I think we jumped out to a few of them, right? Let's let what shall we pop up a poll? You're gonna put them up during the talks, right?
Yeah. Do you have a spot in your, like, do you have any mentions in your slides where they should come up?
No, no. I think the preferred
Ah,
is
okay.
that you just stop me when the next one comes, and I'll let you pop the question up. So why don't you go
Okay.
ahead and
So we'll go with our first poll
yeah.
quiz here. Quantum networks are essential because they, and then it's a fill in the blank here.
And then do you have another one, or are we about to go up to the second one?
Yeah, give me just a second. We're at about 67%. So I'm going to end the poll here and then we can share the results. Ida, you should be able to see the results now on your.
Me? Okay. All right. Looks pretty good. People are doing pretty good.
Okay. Let's go ahead on to our next poll question. Memory enhanced quantum networks transmit qubits using.
All right. Looks like people are doing pretty good. Most people got those answers correct. Um, So let me continue then, and please, like when I guess I didn't put placeholders. So when you see that we're arriving to the next poll question, why don't you interrupt me and let me know, and then we'll put up the next one. How does it?
Okay. Yeah, we'll pop up just after this slide here, I think.
Excellent. Okay, so to summarize, before we jump to we caught ourselves up on the polling questions. When we create these two photons entangled with a qubit, a simultaneous click on both detectors implements a probabilistic Bell measurement. So what will happen is when we take both of these photons and we get a simultaneous click, a Bell measurement is performed on the two photons, creating entanglement between the two qubit states. Now, this only happens when both detectors fire. Otherwise, if a photon was lost along the way, or if we happen to have measured them, in one of the other Bell states, we're not going to get simultaneous detection, and we will end up with an indeterminate result. At that point, we have to go back and try again and look to see if we succeeded the second time and the third time, and we have to repeat this. But once we have succeeded, these qubits are entangled, and then we can store that entanglement because we have a quantum memory and then wait to use it when we need it. And so even though this only succeeds 25% of the time, so it does reduce the rate at which we can generate the entanglement, but once we generate them, we still have that shared resource. And as long as we can generate the entanglement at a rate that is faster than we consume it, we can continue. That's all we need. We don't have to succeed 100% of the times. We just have to succeed frequently enough in order to keep up with the processing of the network. And that's really one of the most important properties of a quantum network. So is this where our next poll question is?
Yes, let's get that next poll question up here. Yeah. Okay, we're gonna go ahead and end the poll here. Share our results.
Yeah. So this one, some people, there's a little more trouble with. So the answer to this one was photonic Bell measurements require photons that are indistinguishable, meaning that they exhibit two-photon interference. So let me just step back and review that. The Hong-Mandel effect only occurs when these photons are indistinguishable. In other words, when they're identical particles. If they have anything that distinguishes them, like polarization, frequency, pulse shape, they will not exhibit this interference. And we will not get perfect HON interference. So for those of you who got it, great. For those of you who don't, hopefully that point clarifies how we get Hong interference. There was another poll question that came up. Is that for the next slide, or are we
No,
ready?
go ahead and keep going. I was premature.
Okay, so now we know the strategy for exchanging entanglement between qubits in a network. We're going to create spin-photon entanglement and use those photons to distribute entanglement between the qubits using Hong-Mandel interference. For that to work, the emitter, the qubit, has to, or the source of photons has to have high purity and high indistinguishability. Purity basically means that it really only emits one photon at a time. Hong-Mandel interference doesn't work very well for random photon number distributions. And so the key here is that we have a really good single photon source. Purity is often measured by something called a Hanbury-Brown twist intensity correlation measurement. The idea is you take your light, put it on a beam splitter, and you look at and you send each port of the beam splitter to a different detector. And the idea here is that if you're really generating single photons, you will never get a simultaneous detection between the two detectors. You will basically get a zero probability of getting two detections at the same time. As you change the delay, the probability will start to increase because there's some probability that the source emitted a photon and then got re-excited sometime later. But what we want from a good pure source is that this drops to almost zero. And typically, the purity of the single photons is limited by either background photons, so background light that you collect, background light from the substrate. If you're using, for example, a solid state emitter that's embedded in a host crystal, that crystal may emit or fluoresce, or multiple excitations. So you're using too long of an excitation sequence. Oftentimes, we excite these emitters with optical pulses. If the pulse is too long, there's a chance you'll multiply excite the emitter. That will also degrade the purity. So the first thing you need is purity. And the second, as we mentioned, is indistinguishability. We need really good Hong-Mandel interference, because if we don't have good Hong-Mandel interference, the fidelity of the entangled state is degraded. And in terms of the actual causes of poor indistinguishability, the typical culprits are spectral mismatch. So your two emitters may not emit exactly at the same wavelength. This is very common in solid state qubits, as Chaohan will explain, because solid state qubits live in different local environments with different strains, electric and magnetic fields, and that can cause slight differences in the emission wavelengths. Even in atomic systems, though, we have this problem. For example, in many cases, you will trap an atom using a strong laser field. And as the atom moves around the optical trap, it experiences a time-varying AC Stark effect that can also cause a spectral mismatch. Polarization mismatch is another thing. So, we really have to control the polarizations, and that can be problematic over a fiber network where polarization can get scrambled. And then there's emitter dephasing. So when a photon gets emitted, it is not uncommon for it to interact with phonons in the lattice if it's a solid state emitter, and that can cause the pulse the wave function of the emitted photon to fluctuate, resulting in poor fundamental interference. So we really need a source that mitigates many of these effects, and I'll talk about it a little bit later. How we can create emitters that don't suffer from these effects as much. So, having gotten a little bit of the background of how quantum networks distribute quantum entanglement, let me move on to the next subject, which is the quantum repeater networks, which are probably were the first examples of a useful function for a quantum network. So, the problem that quantum repeater networks are addressing is that of large transmission losses. If you try to directly transmit qubits through, say, an optical fiber, you suffer exponential channel loss. And the best fiber losses we have to date at telecom are about 0.2 dB per kilometer. So for 1,000 kilometer distance, if you want to send it over 1,000 kilometers of fiber, your transmission is 10 to the minus 20. It is astronomically low. If you want to use a single photon source at a 1 gigahertz rate, creating photons at a 1 gigahertz rate, you'll need to wait 3,200 years for a single photon to make it through the channel. So this is just completely impractical. And if you want to do any kind of fault-tolerant quantum network protocols, you need transmissions greater than 99%, it means you can't go even over a few meters. So this problem is a real bottleneck. And the way that we can get around it is to use a memory-based repeater network. The repeater network overcomes channel loss by transmitting information using sequential teleportation. So in a repeater network, the two people who want to communicate, again, Alice and Bob, the distance between them is spanned by a series of repeater nodes. Each repeater node has two qubits, one to be entangled with the node to its left, and the other to be entangled with the node to its right. And the way that this is going to work is the repeater network will transmit information through sequential teleportation node by node from the sender to node 1 to node 2 to node 3 to node 4, node 5, and so on and so forth. And the way it is done is to first establish entanglement between each qubit in the network and its adjacent node. So for example, this qubit will be entangled with the sender. This one will be entangled with the node to the right. This one will be, and then to the node to the right, this one will be entangled with this one, this one will be entangled with this one, and this one will be entangled with this one, and so on and so forth. And the way we entangle it is using the same strategy that I illustrated a couple of slides ago, which exploits the Hong-Mandel effect. Now, this is a probabilistic effect. So this is a probabilistic entanglement. So you're not going to be able to get everything entangled deterministically in one shot. In fact, each one of these pairs is going to have to try over and over and over and over again. And because of losses and because the Bell measurement is imperfect, they're going to have to keep trying until success. But once they succeed, once this qubit and this qubit are entangled, they can stop and hold that entanglement and store it. And the nice thing is that all of these attempts between these two qubits and these two qubits and these two qubits can be done in parallel. They're completely independent. So all of the nodes in parallel are trying to establish entanglement between the node to the left and the node to the right. And once every time a pair succeeds, they hold that entanglement and store it. And so because we can wait, and then we wait until all of the entanglements have succeeded, this is the important point. In a quantum repeater network, we don't have to succeed simultaneously with all at the same time. We just have to wait for all of the nodes to succeed in entangling their qubits, and then we can move on to the next stage where we perform a local Bell measurement in each node, which requires local quantum gates and Chaohan and Michael are going to explain to you a little bit in their slides about how these local quantum gates can be implemented in solid state and atom systems. But once we implement these local Bell measurements, what we end up with is a pairs of individual entangled qubits in each node, but the end qubits, the ones belonging to the sender and the receiver, are now also entangled with each other. In other words, the entanglement has been swapped from Alice to this node, 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 and finally to Bob. And once the process has succeeded, Alice and Bob have exchanged a pair of entangled qubits that they can now use to teleport quantum information over the channel using only classical communication. And the nice thing about only having to use classical communication is I can now use bright laser beams and optical amplifiers and intermediate classical repeater stations and intermediate nodes in order to transmit that information. I no longer suffer that exponential loss across the fiber. And so this is a pretty amazing outcome because it says that memory allows you to eliminate the loss in the channel. And the more nodes I put here, the faster, the less loss I get, or the faster I succeed. So basically, as I span more nodes here, my channel capacity gets larger and larger and larger because the rate of success becomes faster. But no matter what, no matter how slow it goes, once I exchange this entanglement, I can now deterministically teleport my state from Alice to Bob, and without any problems from losses. So this is a really important example about how memories can be used to transmit quantum information without having to suffer from loss throughout the channel. And so these were the first examples of how a quantum network can achieve an advantage over just simply using direct quantum communication or even exchanging direct entanglement between nodes. Here, we're leveraging intermediate nodes in the network to enable us to do something that we couldn't have done with just a two-party communication system. I'm
Okay,
not
we have a
going to
poll question here.
go
I'll
for
pop
it.
up.
Yeah, thank you. I appreciate it.
And then we also have some questions in the Q&A if you guys want to take a look at those. And I'll go ahead.
Sure. Why don't I take the opportunity? Maybe I'll let me look at the Q&A. Okay, great. So I see. So I think most people got this right. Some people actually. So the answer is that the network, repeater networks exchange entanglement in parallel. That's the key. The key advantage is that we can continue to try to exchange entanglement between pairs independently. We don't have to. We don't have to get them all to work. We don't have to wait for one pair of entanglement to succeed in order to get the next one to work, and so on and so forth. So that's important. Let me look at the Q&A and see. Do you want, how would you like me to do this? Should I answer them live, or should I just type my answers into the Q&A after I've handed off to Chaohan?
It's up to you, however you want to handle it.
Why don't I handle it this way? If I have time towards the end of my talk, I'll discuss some of the questions in the Q&A. If not, I'll hand off to Chaohan and I will type the questions so that you can have your answers while Chaohan is lecturing. So let me jump to the next part of this tutorial. So we got so as I mentioned, repeaters are probably were probably the first example of how a quantum network can do something useful that a simple point-to-point, a simple two-node or simple point-to-point architecture can't accomplish. I'm now going to go over some even more advanced examples of using memory-enabled quantum networks to do things beyond just exchanging qubits or entanglement. So the first example is anonymous quantum communication. So this is an example of a network protocol which, like the repeater protocol, requires multiple nodes across the network. It's based on it requires multiple nodes to interact. So the idea here is that the sender wants to send a qubit to the receiver, but would like to remain anonymous. In other words, the sender does not want the receiver to know who they are, and they don't want the rest of the network to know who they are either. And that's something that classically can't be done perfectly. There are ways like Tor networks and onion routers that try to make it difficult to understand who is sending the message, but there's no way to get 100% guaranteed anonymity in a classical network. But it turns out in a quantum network there is. However, it requires us to actually establish entanglement not just between pairs of nodes like the repeater network. It requires us to establish net entanglement over the entire network itself. In other words, it requires us to establish what's known as a GHZ state, where there's a qubit in each node of the network, including the sender and receiver. And each of those qubits, all of those qubits are collectively entangled together in a state where they're all zeros or all ones. This is known as a GHZ state. And this kind of a entanglement is almost impossible to generate through direct transmission. It really requires many qubits in the network that can store information and successfully exchange it over multiple links. Once this entanglement is generated, then using only classical communication plus local measurements, the sender can actually establish a pair of entangled states with the receiver and then teleport the qubits to the receiver without the receiver knowing who they are. In other words, the sender, the information is publicly broadcast in such a way that only that there's no way for the receiver to know who sent them the qubit, but they know what the qubit value is. And there's a large number of works that have investigated this type of anonymous quantum network. The seminal work is by Gilles Broussard, who proposed the idea way back in 2007. As of yet, I'm not familiar with any network demonstration of this anonymous quantum communication protocol. So it's a big open challenge in the field. A second type of quantum network protocol is distributed quantum sensing. Here we have a bunch of sensors located, separated by large distances. For example, a bunch of antennas tracking an object, or more likely, a bunch of antennas trying to observe signal from a distant star. And the idea is that we want to be able to get all of the signals from these different sensors and combine together to get a maximum amount of sensitivity. Now, if these sensors are not initially entangled, this is a classical sensor network, then the signal to noise ratio will scale as square root of m, where m is the number of sensors. So we get an advantage, but it's a slow buildup of advantage. If we want to get a factor of 10 improvement in signal to noise, we need to increase our sensor number by 100, and that can get extremely out of hand. However, if we initially establish entanglement between the different sensors using a quantum network, then the signal to noise ratio scales as m, not square root of m. And this is a big advantage. If we have 10 times as many sensors, we get 10 times the signal to noise ratio. So this ability to get resolution beyond the classical limit is a major advantage in sensitivity, and one of the main reasons why distributed quantum sensor networks are something that people are actively pursuing right now. Finally, there's distributed quantum computing, an idea that has been around for a long time. The idea here is that quantum computers in their current embodiments are going to have limits as to how many qubits you can pack into a single elementary logic unit. Ion traps can only trap a certain number of ions. Neutral atom tweezer arrays can only control a certain amount of tweezers. In solid state qubits, there's only a certain amount of qubits within our field of view that we can control. We're limited by lasers. So ultimately, we're going to run into some limits. And in order to get beyond those limits, the idea is that we use optical interconnects where the entanglement, where the communication over those optical interconnects proceeds through quantum teleportation, the same way we transmit quantum information over a network. And the nice thing about this is that once you can establish teleportation-based interconnects between different small quantum computers, effectively the distance between them doesn't matter so much anymore. You can have quantum computers in a data center that are connected via fiber. You can have quantum computers distributed over the US map, all working together, provided that you can establish the entanglement between them. Now, let me be very clear. It is much harder to establish entanglement over a nationwide network than it is over a data center. But if that entanglement can be established, then the processors themselves are no longer limited by the physical distance between them. So distributed quantum computing allows you to connect many elementary processors together, and it overcomes the spatial limitations using optical interconnects. It allows you to basically spread them out over larger distances and distribute your resources in a more effective way. It also allows you to make the optical interconnects themselves somewhat functional. You can actually build quantum logic into teleportation. This is work that goes all the way back to the pioneering work of Daniel Gottesman and Isaac Chuang, who showed way back in 1999 that teleportation can be used to implement quantum logic between two qubits that are being teleported, between two qubits, provided that you create a special entangled state to mediate the teleportation that has the logic operation built into it. And so this allows you to actually use these teleportation links, not just to transmit qubits, but also to directly perform quantum logic over qubits separated by large distance. And this has actually been demonstrated both with atomic qubits on a campus-wide scale and solid-state qubits. So people have already shown that you can actually build quantum logic into teleportation and start to actually use these interconnects not just as communication links, but as a part of your quantum circuit. So let me go to the next part of the talk. Here
We
I
have
will.
one poll question will pop up before you go on.
Excellent, perfect. Let's perfect time.
Okay, we're at about 70% almost. Go.
Okay, people did pretty good. There was a little bit more confusion about this one. Only 50% of you got it right. So let me take a couple of step back, and maybe it went quick. So let me go back and discuss this a little bit more because it might have come. Maybe this one came by really fast. In a distributed sensor network, the signal to noise ratio scales as m, as opposed to a classical network with no entanglement that's square root of m. So the signal to noise ratio has a quadratic improvement So in a classical network, multiplying the number of sensors by a factor of 10 gives you only about a factor of 3 in signal to noise, whereas in a quantum sensor network that has entanglement, you get a full factor of 10 improvement. So that was the correct answer to that poll question. All right, let's go on to the performance requirements for quantum memories. So what do we need in a quantum memory in order to realistically implement a functional quantum network that does useful things? And there are a few figure of merits that we have to be mindful of. The first one is obviously the coherence time of the qubit. In a quantum network, the coherence time is very important. It's even more important than in quantum computing. In quantum computing, the coherence time should be long enough to finish your computation. So if you have very fast gates, then you can actually still use short coherence times as long as your gates are proportionately faster. In a quantum network, that's not the case. The coherence time must be long enough so that you can establish all of the entanglement you need over the network. So for example, let me remind you of the repeater network. In a repeater network, we have a sequence of nodes, each one trying to independently establish entanglement. When an entanglement event is successfully established between a pair of nodes, that entanglement has to be preserved long enough for all the others to succeed. If it doesn't, then by the time another pair of nodes has succeeded in establishing entanglement, your entangled pair has decohered, and now you got to start over again. And this could be a kind of, and so if the coherence time is long enough, you're not long enough, you're going to always fail. Every time one node succeeds, another node decoheres, has to start up again, and you're very, very unlikely to have a situation where all nodes simultaneously establish entanglement at the same time. The figure of merit here is that the coherence time of the qubit must be longer than the inverse of the entanglement rate between nodes. In other words, it must be longer than the time it needs to establish entanglement between pairs of nodes. And that depends on the channel losses. The more loss you have in a channel, the more time it'll take you to succeed and establish the entanglement. So so when you're asking how much coherence time do I need, the answer is it depends on how lossy your channels are. And it also depends on how far they are apart, because in a realistic network, photon propagation time between nodes can be large. For example, for a 10 kilometer so for example, in typical entanglement rates in a lab setting, if you have an entanglement rate of 1 kilohertz, this would mean that T2 only needs to be bigger than 1 millisecond, which is not bad. Many qubits have bigger than 1 millisecond coherence times. But in a realistic network, photons have to propagate over maybe 10 kilometers, and that time is about a propagation is about 50 microsecond delay. That's going to increase that's going to decrease your entanglement rate, and it's going to mean that now your T2 is actually going to have to be greater than 50 milliseconds, not 1 millisecond. So it's quite a huge distant problem. And the longer you space out your nodes, the more coherence time you're going to need. So coherence time is very important. And the shorter your coherence time is, the more limited your quantum network will be in range and in its ability to succeed to establish entanglement over all the nodes. Now, how do we improve coherence time? Like if suppose we don't have the coherence time we wanted, there are methods to make coherence times longer. If you can implement them, they're not bulletproof in the sense that they only work under appropriate conditions. But the most common way is to do something called dynamical decoupling. The idea here is to apply a microwave pulse sequence to your spin in order to couple it from the environment, which is what's causing the decoherence. And so the classic example is the spin echo sequence, which basically is a pair of spin rotations followed by three spin rotations that are separated by an equal time delay tau. And the idea here is that when you flip the spin to the equator of the Bloch sphere, over time, fluctuations in the environment are going to cause the spin to slowly dephase. And this pi pulse causes to basically undoes the effect of that environmental dephasing so that you can recohere your spin back to its original state. And so that's effective to some extent. An even more powerful technique is the Carr-Purcell-Meiboom-Gill, or CPMG, pulse sequence in short. This is a pulse sequence that it's been known for a long time. It comes back from the days of nuclear magnetic resonance. And instead of just using a single rephasing pulse, it uses a much more complex sequence of rephasing pulses to continuously flip the spin in different directions in order to prevent it from coupling to the environment. And using this technique, you can increase the coherence times by orders of magnitude. Here's an example from diamond, NV centers in diamond. The red curve here is what happens when you don't use any dynamical decoupling, and you can see that the coherence time is only on the order of a few tens of microseconds. But if you implement a large 20 dynamical decoupling pulse sequences, you can improve that coherence time to over 20 milliseconds. So 3 orders of magnitude improvement in coherence time using these very powerful dynamical decoupling pulse sequences. And so this is just so when you don't have the coherence time you need, hopefully you can use dynamical decoupling to improve you even further, so that you can get coherence times long enough to preserve your entanglement while you distribute it over your network. The other thing we need is photon collection efficiency, which is crucial. We typically generate entanglement through the atomic emission from the same system that is basically supporting the qubit. So for example, if an atom is the spin system that we're using, typically the atom is also the emitter, which emits the photons. And when atoms emit photons, they emit them in all of space. They emit them with no directionality. And what we typically will do is we'll put a lens in the way and try to collect as many of these photons as we can. But unfortunately, even if you get the biggest lens, it's really difficult to collect all the photons emitting 360 degrees. In fact, even with really good collection systems, you typically only capture less than 10% of the solid angle of the emission of the atom. And if you then further want to take this lens and couple to fibers, that reduces the efficiency by even more. And so how do we circumvent this problem? Uh, uh, so how sorry. And then so let me take a step back. So this is one problem. We need good photon collection efficiency, and the other thing we need is good indistinguishability. And indistinguishability is typically degraded by broadening mechanisms in the emitter. For example, if the emitter is coupled to a fluctuating electric field or fluctuating strain field, that will cause the line width of the emitter to become broadened, and that distorts the distinguishability of the radiated photon. And what that basically manifests itself as is an imperfect fundamental interference. So normally, the red line here, with the purple shaded area, should be 0. There should be no coincidences. But because of dephasing, it is only suppressed in a short temporal window proportional to the coherence time, and it actually doesn't make it all the way to 0 because of finite detector efficiency. And so in a realistic system, we need to be able to collect the photons efficiently and also to make sure that they are indistinguishable. And there is a way to do both of these at the same time, and that is by putting our emitter into an optical cavity and using something known as a Purcell effect. When you put an emitter into an optical cavity, you then enhance its radiative emission rate by something known as the Purcell effect. And the Purcell effect increases the efficiency by a ratio which is proportional to the quality factor of the cavity divided by its mode volume. And so if we can get a cavity with a high Q and a small v, we can strongly enhance the emission of the emitter, making it, and then we can also redirect it into a cavity mode that is more easy to collect, has less divergence than 360 degrees. And so that allows us to improve both its collection efficiency and its indistinguishability simultaneously. And here's an example from our group of enhancement of an emitter when it's in an optical cavity. We get a 6-fold enhancement in the radiative lifetime of the cavity of the emitter when it's coupled to the cavity versus when it's not coupled. And also this is associated with a 400-fold improvement in collection efficiency because our cavity is able to redirect, the cavity that we use in this particular case is able to redirect the light very efficiently into an optical fiber. I think I'm going to skip this part since I'm running a little bit behind, and I'm going to jump straight to state-of-the-art quantum networks. Um, so in this final part of the section of the tutorial, I want to talk about where quantum networks are right now. What are the most recent demonstrations? What have we achieved? What haven't we achieved? So here are examples of some of the latest demonstrations of solid state based memory enhanced quantum networks. So these are networks that use qubits that are embedded in a solid. So for example, quantum dots, envy centers. Chaohan will talk about them in more detail in the next talk. And so way back in 2021, there was a really kind of pioneering work from Delft, where they from the Ronald Hansen group, where they established the first example of a three-node quantum network. And this is so it was actually the first time that more than one node has ever been demonstrated in any system. This was done using nitrogen vacancy quantum memories, which are going to be described in more detail in the next talk. This was done, however, only in a meter scale network. It was not done over long distances. However, it's a really important milestone in the field. Another important milestone was done recently, a year and a half ago, by the Lupin group. They changed from nitrogen vacancies to silicon vacancies in order to get a better foot optical interface. And using this approach, they were able to entangle two silicon vacancies over 35 kilometers of fiber in a metro loop. So here, what they did is they had two silicon vacancy qubits. They entangled them with They entangled them with photons, and they sent one of them into a loop, and it came back. It went 35 kilometers out and back, came back to the lab, and got entangled with the other qubit. So this is kind of a big step in that it is using a metro scale network fiber to do the entanglement, but the two qubits themselves were still in the same lab. This has, as far as I'm aware, we still have not yet demonstrated, nobody has yet to demonstrate a distribution of entanglement using solid state qubits over kilometer distances. But we're getting very, very close. This is a very close step. Another work from Caltech, from the Faraone group, used rare earth ion memories in order to distribute entanglement. This is also a lab scale experiment, but it was interesting because it was able to multiplex many of these together, allowing you to significantly increase the rate of entanglement. So the protocol they developed could in principle be used to enhance the entanglement distribution rate. Now, in the area of atomic quantum networks, things have progressed quite a bit further. A few years ago, there was a demonstration of quantum repeater node between calcium ions over a 25 kilometer fiber loop. So already a single repeater node had been demonstrated using a fiber loop for the experiment. This was still done in the lab. However, a year and a half ago, the group from Harold Weinfurter group demonstrated the distribution of entanglement between single rubidium atoms in an optical trap entangled over 100 kilometers of fiber. So this was a 100 kilometer fiber loop entangling two qubits. And then very recently, this is from Janwei Pan's group. They demonstrated atomic ensemble memories entangled over 420 kilometers of fiber, and this was done over a long distance. So over the actual distance was not 420 kilometers. They added a fiber loop, but the two nodes were distributed over about 10 kilometers. But in theory, they could have strung it out a lot further because they actually introduced an additional fiber loop of 420 kilometers, within the network node. So in atomic systems, we're already to the point where we can start to distribute entanglement over memories on the order of tens of kilometers, and there's promise that this could actually be very quickly extended to maybe even 100 kilometers in a larger scale demonstration. And in fact, because of all this progress, there's been a proliferation of quantum networks appearing in various different geographical regions. In the United States, several different institutions have already started establishing local quantum networks. There's QuanNet in California, University of Arizona, and Albuquerque have their own networks. Chicago has established the IEQNet. There's a quantum network in Oak Ridge National Laboratories. Uh, sorry. Here at Maryland, we have the Mid-Atlantic Regional Quantum Interconnect. And at Brookhaven, they have established their own local quantum network. And finally, in Boston, there's the Boston Area Quantum Network. So as the hardware progresses, the infrastructure to deploy it in existing fiber networks and implement quantum networking protocols is also being built up simultaneously. And I anticipate in the next couple of years, we're going to see a proliferation of longer distance quantum network demonstrations. So with that, I thank you for your attention. Let's see. I think right now it's 4:10. I believe that maybe it's best. Chaohan and Michael, how long are your talks?
Well, it depends. Like I can skip some slides. So
Okay, so it sounds like you need to, okay, so let me then just hand it to you because I'm right on time. This is 1 hour and 10 minutes. I'm going to hand it to you and I'll answer the questions in the Q&A by typing rather than through the discussion. So what I'm going to do right now is I'm going to stop sharing my screen and I'm going to let Dr. Q take over and talk to you about solid state quantum memories for quantum networks.
okay, let me start sharing slideshow. Oops, what is sharing? Can you guys see my screen? Okay, let
Yes.
me go back to the first one, first page. Okay, turn on the laser pointer. So should I just go ahead and or like a quick break of like 3 or 4 minutes?
Yeah, I think that's a good idea.
Yeah, maybe we do a 4 minutes break. We go back. I start at like 4:15.
Quick question for the moderator. Is it Brianna? I missed the introduction.
Yes, it was Brianna, and now Belize is going to be taking over for the next portion.
See, I was wondering if we can swap two of the polling questions, just the order of them. in the this is question number 14 and 15.
Okay. Yeah, we can do that.
All right, thank you.
No
That'd be
problem.
great. Thanks.
Also, quick question, for the polling questions, whenever you guys want me to pull up a polling question, can you guys just cue me and let me know which one we're on?
Oh yeah, but it's for my part, I would have poll question at the end because those questions are, I mean, the answer to those questions are quite like separated in different slides.
Okay, sounds good.
So it's at the end, I'll show the poll questions, then you can pop up.
Okay, perfect. Thank you.
So, okay, now it's 4:15. Let's get back to the tutorial. Uh, First, thanks Ido for the very great overview and introduction of why we need quantum memories in the quantum networks. And here, I'm going to talk about like uh, two different types of solid state quantum memories, and that's been used in the demonstration that Ido has mentioned. And for one is a nitrogen vacancy color center, and another is silicon vacancy color centers. My name is Chaohan. I'm a research faculty now working with Ido and Sakai Guha at the University of Maryland. And here's my email. If you have any questions, you can either ask here in the Q&A session, or you can send me an email. Um, so let's start. So this is an outline of my part. So to make the concepts and the physics background go smoother, I'm gonna first start with a quick introduction of the defects in the solid state system that we're gonna begin with the quantum dots, which it can act as a good single photon emitter, but maybe not a good quantum memory at current technical status. And then I'm gonna tell a little bit about the difference between color centers and quantum dot, where the color centers is more like atomic system. Later on, we'll dive into the two main candidacies of the quantum memories. One is a color center in diamond, the NV centers. Another is a group 4 vacancy centers in diamond. I'm gonna talk about like three control knobs for tuning the color centers to meet the requirements of long course time at a reasonable low temperature, and also how we can make the color centers to emit indistinguishable photons, as Ido introduced. That's very important for doing the biostate measurement for to link to quantum node. At the end, if we still have time, I can show some papers that tell you more about the two state-of-art demonstrations of this using color center in diamond as quantum memory in quantum networks. And Ito has already mentioned that. And later on, we have our poll questions. So I will label the take-home message in red. Hope you guys can actually grab that at least, because those concepts I gonna go through, maybe it's a little hard to directly understand when you first see it, but it will like lingering in your mind when you start reading into the papers, and you will have some eureka time to figure out, okay, those concepts really combine together and become coherent. So, a quick introduction to the defects in a solid state system. So, I mean, most of you guys have learned intro level solid state physics, and the research target there is focusing on a perfect crystal system made of periodic atom lattice. It's like this. So you have lattice points forms a crystal structure. So this system has this translational symmetry, which means if you jump from this lattice to the next one, you basically see the whole crystal system identical. You move, you are seeing exactly the same landscape of the potential because the potential is periodic. So by solving this system using like quantum mechanics, the Schrodinger equation, and applying Bloch's theorem, you're basically saying that the electron behaves like waves. So the electron just moving like freely across all the lattice points. This creates bands in the solid-state system. You will have the band gaps that there won't be any electron states in the middle, but you have some bands that will host continuous uh, quantum states of electrons. The issue of this is it's a very boring system. The electrons are like a sea that they're just moving around without forming discretized energy levels. The good thing of using solid-state system is it's actually scalable because that's compatible to the semiconductor industry. But how we can making this system not boring, which make there have some interesting quantum structures. The thing is to induce defects. Adding defects in the solid-state system actually break the translational symmetry. So that will lead to more interesting physics that the electrons just not bouncing back and forth. It basically can be trapped into a local area to form some like two-level system, multi-level systems, and the two-level system can be used as qubits. So if you look at here, this is the structural confinement formed by making tiny structures on your crystal. This is called the quantum dots. In this little hue, like formed by hundreds or thousands of atoms, will actually trap electrons there. And if you consider um, other cases that if you're missing, replacing, or doping other foreign impurities into your lattices, you will create something often called color centers. So here there are multiple types of way to create those defects. For example, you have another atom different than the host material, or like some other vacancy tabs here so that you are missing a host material. The target of having a quantum memory is we need to ensure that the structure has this long coherence time, as mentioned, because you need to wait until you do the Bell state measurement and still have the quantum state saved in the quantum memory to be exactly similar or exactly the same as your original state you want. So I'll talk later to I'll first dive into the quantum dots because it's a more mature system. Quantum dots are good single photon emitters, and it localizes the electron wave function because you create the potential that from a ball crystal into either quantum well, or if you have three-dimensional confinement, you got a quantum dots. And your energy level becomes discretized to be like separate energy levels. So those energy levels can be used as qubits. If you see the SEM image here, you will see that in those semiconductors, you can stack the layers of different material and make them to be this little bump or this little dots there and here, so that those are a confined potential for trapping electrons to follow discrete to feel the discretized energy levels. How you like after you generate these discretized energy levels, those energy gaps will be determined by the size of quantum dots. So if you have a larger dots, that because you have a less confinement in the dimension, which means you will have a smaller energy gap because you can keep more energy levels inside. This will give you the emission light that equal to the energy gap of these confined structures. It will give you more to the longer wavelengths, which is a brighter color. If you have a smaller size, then you can tune it to be into more shorter wavelengths, higher energy photons, and that's blue light. The it's very lucky that because the size of the quantum dot is very small, there's a strong Coulomb interaction so that if you have two electrons inside, they will fight with each other. That means if you electrically or optically pump your quantum dot, you only can excite one pair of electron and a whole pair. And when they recombine it, they will just directly shine exactly one single photon. And using the Hansberry-Brown trace experiment, you will see that the correlations, if you split this coming emitted photon from one quantum dot to two detectors, they will have no coincidence if uh, because you cannot split one photon. So these are gives it makes the quantum dot a really great single photon emitter. So there are a bunch of applications of quantum dots, ranging from the quantum information part that we are talking about to the energy, like in improving the solar cells and also the bioimaging. And it's granted the Nobel Prize in Chemistry in 2023. So then let's see the color center. Uh, As a slice size, those color centers are quite different from quantum dots because the color center is more tiny. They are just created by missing, replacing, or doping like particles in your original host crystals. So it's like a trapped atom inside one crystal lattices. So here I'm showing the nitrogen vacancy center in the diamond structure. And actually, the color center, this name that come from the German word, uh, because in 1930s, people figuring out in the salt that why the salt sometimes show different colors is because there would be some vacancies that in their lattices replaced by only one electron. So here, a chlorine atom has been replaced by one electron, and just because of this defect, it shows the color instead of a transparent salt. Why we need color centers if we already have a really good engineering on the quantum dots and also quantum dots being used in many different areas? The issue is the quantum dots does not really have long coherence time. So let's compare them to the color centers has a smaller size because it's within one lattice. It has an atom-like electron orbit, and the energy level is discretized. For the quantum dot, it has a larger size. It basically in three-dimensional, it's probably 1,000 times larger than the color center. It forms by many atoms to form a macroscopic structure. It has discretized energy levels, but the issue here is because it involves so many atoms, the environment is more noisy. But for the color centers, because it's small and only a few atoms is surrounding it, may give noise to it. It has really long coherence time. This also depends on your host material. So that's why people are lacks the color center in diamond because the carbon 12 in the diamond has basically zero nuclear spin. Later on, we will say that nuclear spin or the other spin paths or the structures will actually adding noise to the system. And that's why we don't like quantum dots used as a quantum memory. However, quantum dots, because it's a macroscopic structure, it actually have a higher emission rate that makes it a very good single photon source. It has also really good to be used in the quantum network for providing ancillary photons. And also its emission wavelengths can be easily engineered, so you can pick the right wavelengths you want. There are a bunch of applications of using color centers in diamond already existing, also in the bioimaging, and to be gyroscopes and magnetic field sensors for GPS-denied navigation. So now let's look into the color centers in diamond for quantum memories. So there are many different types of color centers in diamond. In fact, it's exactly why you can find colorful diamond in this high-end like gem store. Usually, we think of the diamond as perfect transparent crystal, but transparency only happens when the lattice is perfect. The diamond, if it has the high density of like sort of the specific color centers we're showing in the spectrum here, those defects start to absorb or emit light at a certain frequency that gave this diamond a distinct color. To characterize those different color centers, including the nitrogen vacancy center I mentioned, silicon vacancy centers, the better way is to using the symmetry and what atom is doped inside. So basically, uh, if you dope a different atom, it's definitely different because their chemical identity is different, right? The electron orbit around that doped atom will be different. Or if you have a different symmetry, you will always also create different electron cloud around the color center. So here I'm showing that the nitrogen vacancy center is quite distinct from the group 4 vacancy center, which is silicon vacancy, tin vacancy, germanium vacancy, and lead vacancy. Because the silicon vacancy have this D3 symmetry, which if you flip it, it's still the same. But the nitrogen vacancy does not. Nitrogen vacancy only have this threefold rotation symmetry. This also turns into some other features I'll talk to you about is inversion symmetry, making that immune to certain like electric noise. So in this slide, I want to tell you that the symmetry and the doped atom will actually determine the physical property of the color center. So for the nitrogen vacancy center, the structure is quite simple. It's replaced the one carbon, uh, like one carbon atoms in the original diamond lattice is replaced by the nitrogen atom, and another carbon atom is missing. See, this is not symmetric if you flip it so that it has a really large dipole. Looking at this energy level diagrams, no, well, because the Newton center actually has 2 ampere electrons, and it will form this band structure here. And looking at the energy level diagram, we have the ground state here. It's a triplet state, and also the excited state, also a triplet state. So how to understand this diagram is, so the ground state and the excited state, the gap in the middle is the zero photon line. I will explain that later. It's basically an optical transition that is 633 nanometer, and the electrons can jump between those states by absorbing or emitting the photons. Those little tiny lines, you see those tiny gaps to form a group of different discrete energy levels is caused by phonon couple states, because even I said that it's like atom trapped inside a solid state, but it's still not as good as an atom in the vacuum, because if you have temperature, the electron wave function actually couples to the phonon that created by the vibrations of the lattice. The dynamics to describe that, the physics term describe that is the dynamic Young-Taylor effect, and which will create phonon couple state, and so that the state can there will be little tiny gap in those states determined by the phonon hosted by the material. This could cause some troubles when we use it as quantum memory. Another trouble of the NV center is called the intersystem crossing, which happens if you're at this m equal to plus and minus state. The m is the total spin of this two electrons. You will have the chance, actually it's really large chance, that you're going through a non-radiative transition to jump to another uh, manifold, another two-level systems. And that one is emitting the photon at 1042 nanometer. It's not the 633. And then it kind of decay back to your original state. So this intersystem crossing actually, I will talk later about pros and cons of having it. Then to split, so see, this is not a really good two-level system. Actually, for a qubit, you need a two-level system. To really isolate the two-level system, we can introduce extra magnetic field, external magnetic field to create Zeeman splitting, and then you can isolate a qubit. I'll introduce this later. So now, the first concept popping up, and very important to know about the color center, is the zero phonon line. So see, this is the fingerprint of how you measure a nitrogen vacancy center, and this is called using the photoluminescence spectrum, which means in the previous slide, see here, you're pumping this green light at 532 nanometers, is way above into the phonon coupled excited state, and let it decay. What you're gonna see in the spectrum is by measuring using a spectrometer, you will see with a background, a big hue of those photon clicks, you get a little peak around the 637 nanometer. This is the zero phonon line, which means the transition is pure optical. It's actually from the ground state here to the ground state of your ground state. So the ground state, the zero phonon state of your excited state and jump to the zero phonon state of your ground state. This created this little peaks that you're seeing here. Why you got this big broad background hue is because of phonon sideband. See here, you will have a significant amount of chance that your uh, electron at the excited state will jump not to the zero phonon state of your ground state. Basically, it's jump to some state that's coupled to the phonon. So some energy being taken away by the phonon. That's why the energy of your excited photon, when you measure it in your spectrometer, actually have a longer wavelength because it's losing its energy to the phonons. And why you saw this continuous band? First thing is because your spectrometer is limited in its resolution, but another physical reason is you have various of phonon process. You have a ball crystal that it can hold different kind of vibration modes, so that making your fluorescence to be a continuous band. The way to describe that how much light that gonna go through the zero phonon line is called the Debye-Waller factor, and for the nitrogen vacancy center is only 3%. What make it like what's the cons of it? What's the disadvantage having this low Debye-Waller factor is? So imagine you want to emit a photon from this quantum memory that taking away that your state encoded in your state saved in this quantum memory. You have 97% chance that you emit a photon that's not in the frequency you want. You actually emit a photon through your photon sideband, and that's limit your success rate of doing Bell-state measurement later, and also limit your readout efficiency of the quantum memory. And the photon, another concept here is the optically detected magnetic resonance, also we call it ODMR. I want to use this to describe the intersystem crossing. The optical detected magnetic resonance is actually the way to using the nitrogen vacancy center in diamond to sense external magnetic field through Zeeman splitting. Basically, it's looking into the all the photons emitted from the in-wave center after you're pumping it with a green light. But if you put a magnetic wave through the in-wave center close to the transition between the spin state 0 and spin plus or minus 1, you actually will uh, convert some populations of electron into the spin 1 state. This state, if it going excited to the excited state of spin of plus and minus 1, if you go for the intersystem crossing, see here, only the non-zero spin state will couple to the other systems. This will making like 40 or 50% of the light that you originally in the ground state of this ground state to be lost and not gonna give you the fluorescence close to the zero photon line. So that's a way to detect that the popularity of how many states you can flip from the spin 0 state to the spin 1 state. If you have Zeeman splitting, you will see there will be two dips here. If you don't put external magnetic field, you will see only one dip. And using this, you can sense the external magnetic field. The intersystem crossing of the nitrogen weakness center actually give you really high ODMR contracts, so that in the sensing task is really great. But the intersystem crossing actually making you less efficient if you want to read out the spin system. If you consider this to be the qubit that you want to save as a quantum memory, then when you want it to emit a photon, you will have 50% of chance that because the system goes through the crossing, it's not going to give you the photon you want. This can be seen here by recalling how to generate the spin-photon entanglement by the NV. The first thing you initialize the spin state into a plus state between these two spin states. And then you let the spin up state to go a excitation and emission round trip, so it emits a photon. See, now at the beginning it's a superposition of two states. Only you have the spin up will excite a photon into your photonic mode and flying into your network. Then I do a pi pulse, flip it, so that now the previous half superposition part that in the down state now convert to the plus state. And then I do a second round of excitation and emission operation. Then you can generate another photon. So in total, you're generating one photon that is either in the early time bin or the late time bin. We call this is a dual rail photon. And it's now entangled with your original initial state of your spin. Okay. Now, considering that if you have an inter-system crossing that you lost your photon somewhere, you fail this process. Given the efficiency limitation of the NV center, knowing that the low Debye-Bowler factor, making the 97% of the light directly jump into the photon sideband, that's useless. And also you have inter-system crossing that limits your NV center readout. Researchers are looking at the next generation of the defects, which is the group 4 vacancy center in diamond. Silicon vacancy, tin vacancy, germanium vacancy, and lead vacancy. So here on the pinpoint that the silicon vacancy zero photon line is at 737. Yes, the group 4 vacancy center also have the zero photon line because they all couple to the photon. However, comparing to NV, the first thing I want to mention is the bipolar factor of the silicon vacancy or other group 4 vacancy center is almost around 70%, which means you only have 30% of chance each time you excite it into the excited state. Only 30% of the time that when it's jumping back to the ground state, it will couple to the phonon. So which means less phonon sideband. From the spectrum, we can also see that the phonon sideband does not show like a giant heel, but rather a little tiny tail. It has no intersystem crossing. It's determined by its symmetry, and it's determined by its symmetry also because it only has 1 ampere electron, so that spin state is 1/2. That's which means that you probably been able to extract higher generation rate of spin-photon entanglement and don't need to bother about the inter-system crossing. However, there's more features because the group 4 vacancy is one group 4 atom to replace a pair of carbons, but this atom now stayed in the center of the carbon because the group 4 atoms is heavier and larger than the carbon, so it's being like pushed by the surrounding lattice to be in the middle. The middle is the metastable state for it. It has really strong spin orbital coupling, which means the ground state and exact state, even that's just the spin half, is actually will have a zero field splitting without any external magnetic field. You will see the ground state split into two. And this splitting is very sensitive to the string and phonon, and I will tell you more about how to using that as a tuning knob. And actually forms a more like clumsy manifolds than the natural vacancy because now it has 4 energy levels. But considering you have more like adding external magnetic field for Zeeman effect, Zeeman splitting, you actually have more transitions. Those 4 energy levels actually can be resolved if we cooling down the system to a low temperature, because cooling down to a low temperature supplies the phonon sidebands. And then you will see those transitions, and we can actually measure the ground state splitting is 50 gigahertz. So that makes the silicon vacancy has this disadvantage because it can only keep the long spin coherence time below 1 Kelvin. The 50 gigahertz ground state splitting, if you consider working at 4K, 4 Kelvin temperature, you have this thermal photon following the Bose-Einstein distribution. Photons come from the black body radiation, and phonon will come from the lattice thermal vibration. Actually cause random flips because the frequency of those photon background and phonon thermal background has significant popularity at 50 gigahertz. So it will make, if you want to save the information between those energy levels, it's definitely not possible if you're working at 4 Kelvin. The thing is, like, we need to even cooling down to the deal fridge temperature, for example, in the 500 millikelvin, the coherence time will be reached around 10 microseconds. But if you're working at 4 Kelvin, it's basically less than 1 nanosecond. Okay. So here I'm saying that, okay, temperature is a way to control the color centers and making it, especially for the group 4 vacancy centers, to making it to work to be able to work as a quantum memory. However, we need other tuning knobs to encounter the issues, for example, the emission of the color centers to make them identical in the identical wavelengths. And also the other ways is to mitigate some temperature constraints. So why we need to control the color centers? So using color centers as quantum memories, you need considering writing and the reading the spins, right? We need to save the quantum state into nuclear spin to get much longer coherence time. Why the nuclear spin gonna give you much longer coherence time is because the nuclear spin is more isolated from the environment. I'll talk that later in the hyperfine interaction. Another thing we want to control is that we need to compensate the spectral diffusion. We want the light that emitted photon entangled with your quantum memory state, at least the frequency of the photons, we want them to be identical. We already know that you can, similar to the atomic systems, you can do the RF control, microwave control that triggers the single spin, like single qubit gates on a single spin. And what other knobs we can have? The first thing I want to talk about is the string, which causes the deformation of the crystal lattice, which can add to the zero field splitting. If you look into this Hamiltonian, you will see the zero field splitting is this term. If you're adding the string here, you actually can make the zero field splitting different. The Zeeman effect is proportional to your external B field strength, and your hyperfine interaction determined by how good your nuclear spin orbit is overlapped with your electron spin. And this, I'll go forward. So for the string tuning, this is a mechanical process. See, because of even the inhomogeneous broadening or the spectral diffusion of the color center may caused by some unknown local string remain in the lattice, as I mentioned, because the size of the doped atom is quite different from the original carbon atom. So it actually distorts the lattice and different color centers, even that's around the metastable state, but it's still slightly different in their like mechanical tension uh, around that cluster, around that lattice. By fabricating the diamond into a cantilever or bridge, can physically making it bend so that we can stretch the crystal lattice at the atomic level. So this physics deformation changes the local electronic potential and the shape of the electron orbits. Thus, the spin orbital coupling terms will be different. This will directly modify the energy splitting as you see on this measured PL spectrum. You will see that the A, B, C, D terms is shifting. So voltage corresponding to how much bending force you're adding to this cantilever. So the string tuning seems can significantly increase the ground state zero field splitting to terahertz. What's the benefit of that? Recall that you see why we cannot working at 4 Kelvin is because the ground state splitting is only 50 gigahertz. If you make it terahertz, you basically can make it work in 4 Kelvin, but still it cannot work in the room temperature. Another thing that another opportunities opens for doing the control is now instead of using microwaves, you can use acoustic waves. It's the AC vibration that is we call this phonon. Because the silicon vacancy couples really good to the phonon, so you can use the phonon to actually pump the transition instead of using microwaves, and this has been demonstrated in this paper. Another thing is, as I mentioned, the 50 gigahertz band. What if I can create a structure that no phonon gonna exist in this 50 gigahertz band so that your silicon vacancy, no matter what temperature it is, it won't couple to the 50 gigahertz phonons because there's not been able to exist the phonon in this phononic band gap. So then in this paper, researchers has demonstrated the phononic crystal that creates a band gap, actually. And they demonstrate that this can actually enhance the coherence time of the silicon vacancy. The second knob, well, maybe it's not really useful, but we definitely need it, is the Zeeman splitting controlled by external magnetic field. They separate those degenerate spin states so you can tackle them individually. In the silicon vacancy, you now by increasing the magnetic field, you create multiple branches. So they corresponding to different spins and they cross over a certain magnetic field. Then you can use your microwave and RF control to really tackle the transitions that between those energy levels. So you can micromanaging the state that you want. And for the NV, as I mentioned earlier, it's basically give you a way to measure the local magnetic field by checking the ODMR dips. The third knob, the most important one, is the hyperfine interaction. This is a magnetic coupling between the electron spin and the nearby nuclear spin. So here in the NV cluster, you will see if I'm so lucky that I have a carbon 13 instead of carbon 12 around this ensemble, you will actually have the electron spin coupled to the carbon 13 nuclear spin. But still, we will always have this nitrogen 14. It also have a nuclear spin. So you can couple them together and create very interesting energy levels that you can use them to program your quantum memory. It's important to note that unlike string or magnetic field, this is not a continuous tuning knob because it's only when I'm lucky I can find the carbon 13 around it, but I still cannot control that the how much overlap of your electron cloud to this carbon 13 nuclear spin. Currently, researchers is like just randomly picking up those good devices that contains those uh, nuclear spins that they can understand through the ODMR spectrum and using them to do some research. But maybe in the future, advanced techniques in some like fabrications can really putting certain isotopes around the color center memories you want them to couple with. Another quick thing is like in the silicon vacancy, the silicon 29 nuclear spin actually can grant you a really good manifold for encoding your quantum state into a combined two spin state between electrons and nuclear spin. And this also opens up some like RF controls and microwave controls that allow us to do a control not gates between the electron spin and nuclear spin. Let's take an example here. If you just using the RF1 tone to work on your qubit manifold, see if you have a superposition between this state and this state, the up and down state. When you tune this RF1 tune on, and it's basically convert your state by equivalent to have a control NOT gate that your electron spin will control whether you're going to flip the nuclear spin or not. So this is basically a logic gate, two-qubit logic gate between your electron spin and your nuclear spin that can help you to transfer your quantum state in your electron spin to your nuclear spin. Especially in the entanglement generation protocol I mentioned, you can emit the photon, let the photon entangle with your electron spin. Now you can pop the electron spin state to the nuclear spin, then you can have the nuclear spin state entangled with your flying qubits. So and the nuclear spin has a longer coherence time, and that's a win-win. So why do we need? I'll almost go over why we need nuclear spin for color center in diamond quantum memory. The main reason is because nuclear spin is less coupled to the environmental noise, uh, so that you will have a better coherence time. But really look into different quantum memories like NVs versus the group 4 weakness centers, it's quite different. So for NV centers, the main enemy is magnetic noise. The magnetic noise is come from the diamond lattice of random carbon-13 isotopes that act like a noisy magnetic bath, especially for those. So this one is closed, so that you can resolve the uh, the split caused by the nuclear coupled to nuclear spin. However, in a lot of those, because the nuclear spin are far away from your NV center, you basically cannot resolve the energy levels, which means your electron coherence time will be affected. The coherence of your electron state will be affected by the magnetic noise of those spin baths that you cannot resolve. Um, However, if you transfer the qubit into your nuclear spin, then it's immune to other nuclear spins because the coupling between nuclear spins to other nuclear spins is really small. And you can make the storage time from milliseconds to seconds and even to minutes. And also, you can also free the electron spin for other tasks like sensing or doing another round of the entanglement generation. On the other side, for the group 4 vacancy centers, the actual enemy of the coherence is thermal noise. At 4 Kelvin, the thermal photons will cause electron orbit state to mix. Uh, so if that's why we cannot keep the quantum state when just in the electron states. We want it to be converted into the nuclear spin because the nucleus has no orbital angular momentum and it physically cannot couple to the photons. So you free up your electron spin and you also have your nucleus more tolerant to your like thermal photons. So then your quantum memories can go to milliseconds level to seconds level coherence time. And here's we can also implement the dynamic decoupling introduced by Professor Ido Wax in the previous talks, and this can extend the coherence time to the state-of-art 2 seconds, and which is still much longer than if you want to save it in the electron spin. Even you save in the electron spin, you can apply dynamic decoupling, but it's limited to around 10 milliseconds. So still, saving in the nuclear spin give you advantage in the saving in the coherence time, at least in the silicon vacancy centers. So now we have a little bit of the time so that I can go over some state of our demonstrations of these two kind of color centers in diamond for the quantum networks. The first group of seminal works is from TU Delft. It's using the NV center in the bulk diamond. Uh, their secret techniques is this solid immersion lens. So the natural vacancy center itself originally limited in its efficiency of generating photon spin entanglement. Uh, Another limitation is like in the bulk diamond, similar like the atoms, the light is emit 360 degrees everywhere. The trick to collect enough photon is to putting this immersion lens is by etching down your diamond to looks like a ball lens to really collect the silicon vacancies into your collection optics. Uh, Professor Ido Wax mentioned why we cannot use the cavity for nitrogen vacancy center. That's because the nitrogen vacancy center has a really large dipole. It's not inversion symmetry. I recall the symmetry of the NV centers. It's only have the rotationary symmetry. If you have a charge, a DC static charge or DC voltage, nearby it, it will actually shift the zero photon line of it. because it has a really large dipole caused by it lacks the symmetry. So that if you put inside the cavity or any other nano structures, those structures will accumulate charge randomly in time. It will take charge and throw it away, so that in the time you will see that the your natural vacancy emission zero photon line is jittering. It's changing. It's changing by a few tens of megahertz, kilohertz, and greater it could be gigahertz. So that's not going to be used good as a stable quantum memory. So that they put a solid immersion lens to try to enhance as much as they can of how to collect the photon. But because natural vacancy is limited by its efficiency, intrinsically by the bipolar factor and also the inter-system crossing, the entanglement rate, even over the 30-meter links, is only 10 hertz, 10 pairs of entanglement pairs generated every second. And if you consider the two links, it's less than 1 pairs in 40 seconds. On the other side, in the Boston area, the Boston testbed, the looking at Lonkar group in Harvard University are trying to use silicon vacancy to encounter the inefficiency of the natural vacancy center systems. Their idea is to having this integrated photonic crystal cavity. So the silicon vacancy here has this inversion symmetry so that it's immune to the charge that accumulates along this structure, which give you more better stability in its zero photon line, the emission wavelength. So you can easily put the silicon vacancy into this integrated cavity that create Purcell enhancement and further to this strong coupling regime where your cavity reflection rate, actually the transmission, if you are sending a photon in and bouncing back, the transmission of this photon is actually determined by your spin state. If you're in a spin state here, the cavity will work like a absorber, so that no matter how many photons you shine there, the cavity will absorb it. However, if you're in another state, the cavity resonance shifts because of strong coupling. The cavity mode is strong coupled to the your electron state. Then the photon will be reflected. So using this method, you actually create a control transmission gate between the photon and the spin state. And this is basically the phone gate they're showing here, so that they can translate the nuclear state and electron state to the photon state, and to do a similar type of Bell state, like entanglement distribution and Bell state measurement along this way. They achieve entanglement rate much higher than using NV. They reach 0.25 pairs per second over 35 kilometers. The 35 kilometers is a huge amount of loss across the Boston telecom fiber networks. So that's all about the color centers used in the quantum memories. And here comes our poll questions. Yeah, you can check the slides.
So I'll do poll question 6 first, give time
Okay.
for that, and then I'll do poll question 7 after.
Mhm.
Okay, and then I'm gonna queue up poll question 7.
Yeah, I can explain this first. Yeah, you guys did really great job. So it's true that 50% people select the right one. The operation at room temperature is not an advantage. I can explain why others are the advantage. The very long coherence times, because you can use hyperfine interactions to make the quantum states stay in the nuclear spin, encoded in the nuclear spin. The efficient spin-photon interfaces is because this is a little tricky. I should mention here is because you have the better way to have either solid immersion lens or a cavity to integrate with your color center. So it's sort of efficient, but I understand that it's a little distractible, and people select this one maybe considering the envy centers that because the photon sideband that's you cannot make it really efficient. But that's the efficient that's the inefficiency is in the spin photon entanglement generation, but the spin-folding interface is pretty much efficient. The good scalability is guaranteed by, at least for now, we understand um, that it's following the standard of semiconductor industry. We will try to make it CMOS compatible, and but there's still some time to make it really scalable. That's why in the network demonstration, you see only limited numbers of nodes or numbers of color center being used. The operation at room temperature is usually not possible, both for NV and silicon vacancies, because that will severely affect your coherence time. The NV electron spin have good coherence time in room temperature. However, in the room temperature, it just uh, have other broadening that if you dive into that, you will know better than the poll question 7. Okay, it's a little trickier here. So what's the approximate zero phonon line emission wavelength of the silicon vacancy center in diamond? The right answer should be 737 nanometers. So this is a fact. If I go back to the slide, um, here, you will see a silicon vacancy zero photon line around 737 nanometers. Uh, okay. Let's go to next poll questions. Next two poll questions are this. Yeah, for this one, 50, yeah, most of the people select the right answer. It's 637 nanometer. So I understand some of them may answer 1550 because I mentioned that there were telecom network demonstrations. They are using the frequency conversion technique to convert 737 nanometer light emitted from silicon vacancy into 1550. For the nitrogen vacancy around 637 nanometer, you might need, uh, people haven't demonstrated that been converted to 1550 nanometers in the quantum networks, but it's possible. Yes. The hyperfine interaction is actually the interaction between electron spin and nuclear spin. And this allow us to transfer the state. I basically do the uh, two-qubit gates between electron spin and nuclear spin. So you can transfer the information or quantum state between them. So the final two questions is a little challenging. Oh, yeah, this is a very challenging questions, and I think I'm mad because I didn't really emphasize the string tuning. So if we go back to the string tuning section. It indeed, actually, I understand why a lot of people select the D. I think that's also correct, because it's actually changing the energy gap between the ground state and excited electric states. From this figure, you can see that it's changing the ZPL. That's a yes. So I think this should be a double choice. But my intentionally consider is the C is also correct because uh, in the percentage speaking, the string actually directly changing the zero field splitting, which is, you see in the percentage, this difference has been changing more prominently if you apply string more and more compared to the relative change in the wavelengths. The wavelength is mainly changing a few nanometers, so it's less than 0.1% probably. But basically, the spin orbit induced splitting is changing tens of times or even more. Thanks. And so next poll questions, it's better you see. Oh, I think if it's better to read the poll question 11 uh, on the slides. I think the version is a little bit different. Uh, yeah, there's a little tricky thing when I put this poll question there. Yes. Uh, so the B should be, I don't know why I dropped this in the middle there. The B is not true. NV center is formed by replacing two neighboring carbon atoms with one nitrogen atom at one carbon site and another carbon site to be a vacancy. The pop-up poll answer is a little bit uh, uh, erroneous there, and it has a correct label there. But I want to add a little more to emphasize the other answers. So the A is definitely correct. It's sitting in the middle, uh, two vacancies around it. That's a silicon vacancy. C is correct because the silicon vacancy center has its inversion symmetry if you rotate it along one axis for 180 degrees. This makes it immune to the DC static charge. You consider a static charge create static electric field. Uh, if you integral a symmetric electron orbit around it, you will get zero. The first outcome will be zero. The D, both silicon vacancy and NV center typically require cryogenic temperature to achieve long spin coherence times. I put a partial yes here because in demonstrations, we all want as long as possible for keeping the information in those quantum memories. So we want to reduce the thermal phonon. We also want to reduce the thermal photon. And by doing that, lowering the temperature is definitely the right way to go. The NV centers, as I mentioned for previous poll questions, can keep good coherence times in room temperature, but we won't say it's long enough. And there are also other noises to make it not just coming from the standard decoherence from coupling to phonon or photon, is coupling to other like noise in the lattice. Okay, that's it. If you have further questions or suggestions, please contact me at my email. If you can also put your questions in the Q&A session, and I'll try to answer them while I pass to Michael.
Okay. I think so. I do have the poll questions on my slides, so they should be straightforward where they land. I think I'm going to start maybe in half a minute, give it people a break, but I hope we could end on time, so I will not to take too much of a break.
Okay, sweet. Yeah, just cue me up whenever you're ready for your poll questions and I can put them on the screen.
Okay, sounds good. Thank you.
No problem.
Okay. Hello, everyone. Thank you, Ito, and thank you, Chaohan, for handing off to me. My name is Michael Kwan. I am one of Ito's grad students here at the University of Maryland. And for the remainder of this lecture, I will first provide an overview of a different type of quantum memory that is often used in quantum networking, and that's different than the ones previously discussed. That is the atomic quantum memory. This would be followed by a deeper dive into a specific subset of that, the trapped ion quantum memory, and its role in long-distance quantum networking. So, atomic quantum memories store quantum information using single or ensemble of atoms. The two most commonly studied categories of atomic quantum memories are ions, and shown on the left-hand side, and neutral atoms, shown on the right-hand side. In the context of quantum networking, we focus more on the atomic ions. Molecules and molecular ions are often explored in the context of quantum chemistry and simulations, at least for now. So we're not discussing those much here. And because we're not discussing molecules here, we can say that each atomic memory is comprised of atoms or ions of the same element and the same isotope. For example, we have cesium-133 atom or the ytterbium-171 ion. Now, as you can see, atomic quantum memories are fundamentally identical and not subject to differences in fabrication. A ytterbium-171 ion in one lab is the same as another one halfway across the world. This also means that entangled photons emitted by the same type of quantum memory are, in principle, indistinguishable. Unlike solid-state quantum memories, ions and neutral atoms are not embedded in solid materials for indefinite storage. Instead, they're trapped and suspended in vacuum as needed using a combination of electromagnetic fields and lasers. This means that they're extremely well isolated from nearby atoms, but on the flip side, they require a certain level of vacuum to operate. Otherwise, background gas particles just collide and knock them out of their traps. So I'm going to go a little deeper in the trapped ion side now. Trapped ions are confined either with Paul traps or with Penning traps. With a Penning trap that's shown on the right-hand side schematic, it works by having electric fields on the electrodes directed towards the middle in the radial direction, combined with a magnetic field along in the axial direction in a cylindrically symmetric trap configuration. Paul traps, on the other hand, confine the ions in potential wells using a combination of DC static electrodes and AC electrodes, whose electric field contributions vary at radial frequencies, typically tens of megahertz. And so I'll refer to these electrodes as RF electrodes. For the remainder of the trapped ion discussion, I'm going to focus on Paul traps since they're more widely used and especially in ion experiments with high degree of control of individual ions. Another reason to focus on these Paul traps is that you often find adaptations of them in fields outside of quantum networking, such as in residual gas analyzers. So they're widely applicable. The Paul trap shown here is one used at the University of Maryland. You'll see in the magnified image that on the right that the DC electrodes are 5 segmented blades. In the side view, you'll see that another set of DC electrodes are hidden in that view behind So if you're looking at the 0.6 NA direction, behind the set of RF electrodes. And so diagonally across. Segmentic electrodes, they help allow us to tailor the deepness of the depth of the potential well and how closely spaced we want the ions. This trap is called the linear Paul trap because ions are trapped in a linear chain. Other ways of assembling a Paul trap include using 4 rods. This trap is often called a rod trap or quadrupole trap or surface traps. With the surface trap, it is microfabricated, so it reduces the imprecisions compared to when assembling millimeter scale rods and blades by hand. And moreover, they typically have many more electrodes, and which allows us to do fancy manipulation like shuttling ions around, which can be important for scaling up locally. One disadvantage of the surface trap is that potential wells are relatively shallow because the electrodes are not cylindrically symmetric. You don't have electrodes on top of the ions. So you might have noticed by now that both the Penning trap and all variations of the Paul trap require more than just a static electric field to confine the ions. In the Penning trap, it is an additional magnetic field. In the many Paul traps, it's an additional RF contribution. This is because of Earnshaw's theorem, in which Earnshaw proved that there are no stable equilibria for charges in electrostatic fields. There are only saddle points at best. In the mechanical analogy depicted on the left here, where the ball represents the ion, it can only remain trapped if an oscillatory field is applied, spinning the saddle around on its axis. This is an informal but hopefully intuitive explanation of how ions are trapped in these traps. Formal solutions of the trapping locations and depth of the wells, that depth is also called the trap depth, can be found by solving the Mathieu equation with the relevant input parameters, the R naught, ion to electrode distance, U and V, the DC and RF amplitudes respectively, and omega, the RF frequency, also the charges and mass of the ions. Now, the Mathieu equation has both stable and unstable solutions, so we usually want to work backwards from the desirable stability parameters A and Q that are in the gray region, and then to numerically determine what voltages and frequencies we need to apply to the electrodes. While the RF voltage amplitudes vary greatly among different trap geometries, the DC amplitudes are usually on the order of volts, and the RF frequencies are usually between 20 and 50 megahertz. As mentioned before, ions are trapped as needed. Unlike solid-state quantum memories, and unlike neutral atoms, which I'll talk about a little later, which are stable on their own, ions interact with electric fields and other charged particles. The advantage is that you can use electric fields to trap them, as discussed before. But the disadvantage is that the ions bind to other particles or to the walls of the system once the electronics are turned off. The consequence of this is that we need to load the trap at least every time we turn off the electronics and turn them back on. There are 2 steps to this loading procedure. First, we need to generate the atomic beams directed at the trapping region. This is commonly achieved using a resistive oven or ablation. Once the generated atomic beam fires across the trapping region, the atoms are ionized using specific lasers that are specific to each element. Resistive ovens are often simply just stainless steel tubes, about 1 millimeter in diameter and about 10 millimeter in length, welded to a long copper lead. An optional tungsten filament can be attached between the copper and stainless steel oven to decrease the current needed to generate a gaseous plume to sublimate, basically, the sample. A solid sample of atomic source is such as barium or ytterbium, is placed separately into each oven. Those are located here. And the other end of the copper wire is attached to the oven, the vacuum feed-through out of the system. You'll notice on this image that we have ceramic beads or Kapton coating that insulates the copper leads to ensure that all the current is flowing to the oven, not to the ground of the trap. A current supply is attached to the outside of the feed-through to a corresponding pin to supply several amps of current to the oven. The tip of the oven is usually about 10 to 20 millimeters away from and directed at the trapping region. With this method, the center of mass speed of this sublimated plume is around 300 meters per second. One drawback of this loading method is that it is relatively slow. It takes maybe about a minute or two before the oven gets hot enough to generate enough atomic beam. Hot enough to generate an atomic beam. But it is only necessary to retrap once the ions escape. So this could really mean, just running the oven once or twice a day. Now, ablation loading relies highly on high-powered laser to sublimate the atomic source. A solid sample is placed behind a cavity in the wall of the interior to a chamber, usually at the similar distances as traditional ovens. And here on the left is a photo of two adjacent ablation targets sitting about 10 millimeters from the trapping region. Then typically a pulse laser of millijoules peak power is directed towards the target and sublimates the sample. The threshold fluence, it's been studied that at which a sample would sublimate is around 0.2 joule per centimeter squared and may vary with the atomic source used. With this method, the center of mass speed generated is about 500 to 1,000 meters per second, which is greater than the oven method, depending on fluence. This method of loading is much faster, on the order of seconds, but a drawback is that it's less directed because there is a limit to the Rayleigh range, which is the range at which the laser stays focused. And so it cannot be deep inside the tube, or else the laser could not effectively sublimate the atoms. So it tends to coat a lot of the other surrounding areas in the chamber. So after generating the atomic beam, we go to photoionization, which is a two-photon process for most, if not all, ion species, because a single ionization requires lasers deep into UV, and those aren't readily available. The first photon must be coherently excited to the excited state, but then the second photon needs only enough energy to eject the electron. As a result, there are clever schemes that you can use to save on different lasers. For instance, the 413 lasers, the 413 method of ionizing. If you go that path, you just need another 413 photon to kick it out of the to ionize the atom. That saves you another laser. Similarly, in the ytterbium case, the 399 as a first step gets it to the excited P state. Ytterbium has another service beam that uses 369 nanometers. And because of that, you can use that laser to directly kick this and saving you another laser that you need to get to do the ionization, and you need to align to the trap. Photoionization is also where the specific isotope is selected. The line widths of the first steps of these transitions are far enough apart that being on resonant with one isotope would usually not accidentally ionize another one. With similar reasoning, singly ionized atoms would not doubly ionize simply by leaving on the photoionizations too long. After ionizations, the ions do not automatically stay in the trap for a long time. They usually still have very high kinetic energy because it's a gaseous plume at hundreds of meters per second. And the trapping potential alone cannot confine them. Doppler cooling is used to cool the ions to the Doppler cooling limit. It exploits the imbalances between the ions scattering to slow and the ions and confine them within the trap. The Doppler cooling beams must have non-zero components on 3 trap axis dimensions to effectively cool the ion. In the case of the barium-138 ion, the Doppler cooling beams are 493 and 650 nanometers, since about 25% of the time, the P1/2 state decays to D level, and the D level has a long lifetime. So you must have a 650 repump beam to bring it back to the P state so it falls into the ground state. For 174, ytterbium-174, and likewise for 171, you have a much smaller percentage, only a 0.5% chance that it decays to D state, but you still need to kick it back out. That difference is what gives rise to a very nearly perfect state detection mechanism because of this very low probability of decay into the D state in ytterbium. The colors needed are 370 and 935 here for ytterbium. The Doppler cooling limit for both ions are on the order of millikelvin. And if you want to cool it further, you can use resolved sideband cooling and to reach 0 photon state where you want to be at to perform qubit gates. Now, cooling to the Doppler limit does not mean you can just turn off the Doppler cooling beams. All traps have anomalous heating that heats the ion up 10 or to 1,000 quantas per second, depending on the type of trap, the trap geometry, and the ion distance to electrodes. And leaving the Doppler cooling beams on combat this rate of heating. Another mechanism that limits the trapping lifetime other than the heating rate is collisions with the background gas. Room temperature systems, such as one on the left, require ultra high level of vacuum at or below 10 to the minus 10 torr. To reach that level of vacuum often requires a long bakeout process on the order of week. Alternatively, ion traps in cryogenic systems, like the ones shown on the right, have relaxed vacuum requirements for the same background gas density. This is because at cryogenic temperatures, the background gases are much slower and will adsorb to the walls, and so less likely for interactions with the ions. Both room temperature and cryogenic systems can keep ions for days, but cryo systems have longer trapping lifetime in the dark, meaning with all the lasers turned off, because the heating rate is usually also lower. Now, so far we covered the mechanics of trapping ions. Take a quick second to answer this poll question before we have a mini review. Okay. Okay, yeah, because trapped ion has a lot of overhead in the equipment needed, so it's easy to get things mixed up. The correct answer here was D, ablation and resistive heating. Resistive oven. And let me close this window. So in summary, it's good that we have a summary of this. When you have a Paul trap, you first need to package it in the appropriate vacuum system with the corresponding feed-throughs, then simulate the packaged trap electrodes, DC and RF voltages, and apply them to the electrodes. Next, you'll need to generate the atomic beam using either the ablation technique or resistive ovens, followed by two-step photoionization, and then Doppler cooling. Yeah, so there's quite a bit of experimental overhead. And I'll try to, and that doesn't even include the state detection, photon collection, and magnetic field application that we will discuss in a bit. Yeah, maybe I can also slow down a bit. As with diamond vacancies, we can apply magnetic fields to generate a ground state Zeeman splitting in ion species that are well suited for it. The magnetic fields are typically applied using coils with current running through them, or even small permanent magnets, since typical magnetic fields are on the order of several Gauss. On the other hand, hyperfine ground state ion qubits, such as ytterbium-171, are insensitive to small external magnetic fields, like Chaohan mentioned. There are also optical and long-lived metastable qubits in these ion species, as well as a host of others. They can all be trapped using the Paul traps and using the recipes outlined in the previous slide. They also have the potential to be quantum memories or serve other purposes for quantum networks, but they need to be further studied for those purposes. While we're on the topic of quantum memories, I should also point out that some ion species are well suited for qubits, which are generalized qubits. Instead of mapping the quantum information from to a superposition of zeros and ones, qubits map the information to a superposition of 0, 1, 2, 3, so on to d minus 1 for a d-dimensional qubit, allowing us to store much more quantum information. However, harnessing that extra quantum storage space requires even more overhead. Like optical qubits, the use cases of that in quantum networks need to study further, but just want to let you know that they are something that are current topic of research in trapped ion quantum memories. So what are trapped ions capable of? First, gates are performed using the collective vibrational modes. So the ions must be cooled to a few phonon, meaning minimal vibrational level, to perform high fidelity gates. Trapped ions have some of the highest single and 2 qubit gate fidelities, with the 2 qubit gate exceeding 99.97%. Long coherence times have been demonstrated in hyperfine qubits, which are more robust to magnetic field noise than Zeeman qubits. This particular hour-long coherence time was demonstrated in ytterbium-171. Finally, the state-of-the-art number of trapped ions in a single trap is about 500. Now, a quick comparison with neutral atoms. I'm not going to spend too much time on this, but just a brief comparison. Neutral atoms, on the other hand, are confined in magneto-optical traps, where 3 orthogonal pairs of counter-propagating laser beams of the same color work in conjunction with a very weak quadrupole magnetic field to slow the warm vapor to microkelvin levels and to essentially trap the atoms there. Then the atoms can be manipulated using finely focused laser beams known as optical tweezers, to interact with every other atom in the trap, not only the nearest neighbor. Common neutral atom species are chosen for their hyperfine structure. These include cesium-133, rubidium-87, rubidium-85, and more recently, some of the ytterbium isotopes as well. What neutral atoms excel at is scaling up in a single trap. The state of the art is about 6,000 cesium-133 atoms. Relatively high single and 2 qubit gate fidelities have also been demonstrated. And a record coherence time in neutral atom is 12 seconds. One of the challenges in neutral atoms is the state preparation time due to the destructive readout, where the trap needs to reload between state detection cycles. There's ongoing research to speed this up with non-destructive readout methods. Compared to neutral atoms, ions don't scale as well locally, but a lot of progress has been made using the quantum QCCD architecture. This architecture involves using surface traps to shuttle ions to different zones. This maintains the all-to-all connectivity and is well suited for performing high-fidelity gates and uniform gate operations and readout at the respective interaction zones. So you have an interaction region, you have a memory region where they cool and store things. Some challenges to local scaling include, like mentioned before, anomalous heating. Surface traps specifically typically have a higher heating rate than other macroscopic Paul traps due to their proximity, the ion proximity to the electrodes. Another challenge to scaling is excess micromotion. When the trap isn't shielded properly from stray electric fields, and that becomes harder to do as you scale up, the trap DC null drifts from the RF null. Then there will be a small amplitude of motion at the input RF frequency, known as excess micromotion. So an alternative, but perhaps also complementary way of scaling, and is also the backbone of quantum networks, is by using photonic interconnects, also known as flying qubits or entangled photons. The benefits of this method are scaling, supporting long distance networking on the order of kilometers. And it allows for hybrid networking with other trap types, other species, other ion species, atom species, color centers, and allows connecting to integrated photonic devices, such as the straightforward photonic switch here designed by one of our former group members. And lastly, we can do this scaling up by using some of the existing fiber infrastructure at telecommunication wavelengths. So I have 2 poll questions here, just as a checkpoint. Yes, all of the above. So given, many people got that right, I expect the next one would also be quite straightforward. Yeah, a Zeeman ion and a hyperfine ion. So maybe I could go back. So the answer is barium-138 and ytterbium-171. This question is asking to see whether you recognize that there are barium isotopes that are hyperfine qubits and ytterbium isotopes that are Zeeman qubits. So whether they are Zeeman qubits or hyperfine qubit depends on whether they have a nuclear spin. So, for example, 174 does not have a nuclear spin. So it is on Zeeman qubit, even though it's a ytterbium ion. And whereas 137, barium 137 has a nuclear spin. So it is has a hyperfine structure in the ground state, at least. And so it isn't hyperfine ion. 138 is the Zeeman ion that I've been referring to most, and ytterbium 171 is the hyperfine ion I've been referring to most. So, so that networking architecture is actually one suggested by Dave Weiland and Chris Monroe a few years back. And in the following discussion, I'll focus on this dual species networking architecture that involves the 171 ytterbium and as a computational qubit, and the barium 130 as the communications qubit. The role of barium here is to perform local gates with the 171 ytterbium ion to obtain the quantum information that it has and transmit it throughout the network with help of entangled photons. And why barium 138, not other isotopes or other species? It's because entangled photons can be generated at relatively high rates. Recall the 75% probability of decaying to S state and 25% to the D state. Well, ytterbium has 99.1. That's because we don't use ytterbium there because it will be in the very UV. It's a 369 transition. Yes, it will have a larger branching ratio, but it would also be further from the telecommunications wavelength. Even this is a problem because we're at 493 nanometers and telecommunications usually at 1550. But I will address that problem a little later. So, but first I want to talk about how entanglement, ion photon entanglement is generated. We have to first understand that coherent light of a specific frequency and specific polarization excites an ion population from one state to another. In the upper excited states, the ions can decay spontaneously or stimulated to any allowed state on the lower energy level. For example, the mj plus 1/2 state can spontaneously decay into either the S of the S 1/2 states. So for some context, because of the presence of this magnetic field, this leads to the quantization of the angular momentum. So the ion, what the ion sees circularly polarized light as sigma light, which increases the angular momentum, sigma plus light, which increases the mj from negative 1/2 to 1/2, meaning increases by 1. Similarly, sigma minus light decreases mj by 1. And if the electric field is quantized along the quantization axis, then the ion sees this as pi light, which does not change the mj when shown on it. So with that, there's also one more piece of information you should know before attempting this, is that the lifetime of the P1/2 state in barium is about 9 nanoseconds. And the lifetime of the D3/2 state is about 80 seconds, which we can consider as infinite compared to the P1/2 excited state. Therefore, in the typical experimental cycle, about a millisecond, it can be considered stuck there until a laser repumps it out of the D state, if it lands in the D state. So with that information, try to give this, I noticed that the Greek symbols aren't showing up. Okay, but they should match the ones on the screen. So maybe try reading on the PowerPoint. Take a little bit more time with this because it does require some thinking. So we can eliminate A because if you remember the main P to S transition is 493 nanometers, and the repump from P to D is 650 nanometers. C and D, they both have sigma minus, which tends to lower the MJ of the excitation. So, for instance, in C, you would have the atom ending up in not only the M minus 1/2 state of the S 1/2, but also the M minus 3/2 state of the D 3/2. Yeah. And so this is actually where we're going next. So in order to pump to this state, we have to turn all three beams, this 650 sigma and 650 pi and 493 pi light on. To ensure that 493, to ensure that none of the population stays in the ground state, and the 650 pi light ensures none are in the middle two states, and sigma plus ensures that no population of the ion is left in the negative 3/2 MJ of the D 3/2 level. So that is actually the first step of generating ion photon entanglement, because we want to shelve it away to somewhere where then we can excite it and track where the photon is coming out of. So once we have it at M equals 3/2 of the D 3/2 state, you can do a pi over 2 pulse of 650 sigma minus light, and to bring it to the M 1/2 state of 6p 1/2, and that will spontaneously decay to either 0 or 1. Now, the branching ratio of the two ground states are root 2/3 and root 1/3, so they're not equal. However, just like in the case of the ion seeing something different because of the quantization axis, we can collect orthogonal to the quantization axis. And by doing so, we sacrifice 1/2 of, we sacrifice 1/2 of the sigma plus light, so that it becomes a true Bell state, a maximally entangled state here. So that's how we generate the 493 entangled photon. So that photon, the spin of the ion is entangled with the polarization of the photon. Now, to verify that entanglement, we have two metrics. The first metric I'm going to mention here is the fidelity. In this paper here, the demonstration of atom photon entanglement, the authors show that it suffices to just determine several elements of the density matrix to determine the upper and lower bounds of the ion photon entanglement. So you don't have to do a full tomography of the state to measure exactly what the fidelity is if that's not what you're interested in. However, if you are interested in that, you need to do a full tomography, which means measuring in every basis, both the photonic qubit and the ion qubit. So with this bounding method, we only have to measure in the diagonal state as well as the original states. What I mean by that is, so in the original state, the ion basis is 0 for no fluorescence and 1 for yes fluorescence. And in the photon basis, it is H and V. And this is a beam splitter, which transmits H and reflects V. So you could sort of discriminate between the states in the original unaltered basis. Now, these rho tildes are basis elements, so are density matrix elements measured in the rotated basis, rotated by pi/2. So to rotate that, you need to, for the ion, you need to use an RF antenna at the 14.65 megahertz, which is the splitting of the Zeeman splitting of the two ground states, and do RF rotation. For the photonic qubit, what you need to do is a half wave plate rotate the polarization by 45 degrees, and there you are in the diagonal and anti-diagonal basis. And for the ion, you're in the plus and minus basis. And then you do that measurement again using fluorescence and the beam splitter. So you measure those populations, they give you a number between 0 and 1, and plug it in here, and that'll give you the fidelity, which measures how good your entanglement, ion photon entanglement is. Now, it is ion photon entanglement at 493. So this is only at 493. It is still far away from where we need to be at telecom for all the benefits we mentioned above about connecting to other systems and transmitting through fibers. Here we need to enlist the help of quantum frequency conversion. It is most frequently done using nonlinear Chi2 material, such as piplins. These are quasi-phase match by temperature to the Chi 333. And based on the conservation of energy, we have this relation between the initial wavelength, the pump wavelength you need, and the target wavelength you need to reach. And the conversion efficiency is defined as the efficiency of the power, as the ratio of the power normalized by the wavelengths of the target versus the input with input photons. And here we see the agreement between the classical and the quantum results of the frequency conversion. Notice that the efficiency is a function of sine squared of the power. So that tells us that there is a maximum power of pump photons you put in, such that you get a peak conversion efficiency. And if you put more power above that, it starts to, the efficiency starts to go down from the peak. So that would be important in verifying we have the right setup. So another poll question here. So we have a pump laser at, so we want to find a pump laser that takes us from 780 nanometers to 1283 nanometers. Oh, and I think I forgot to remove the correct, so yeah, okay. All right, yeah, so very straightforward, apply this formula and you'll find that you need a 1989 pump to convert 780, and it's expected that 1989 is lower frequency, lower frequency, longer wavelength than both either of these, because we're going down in frequency down conversion. Some considerations when setting up QFC systems is that you want to eliminate noise photons, and two main sources of noise come from spontaneous parametric down conversion, where you have pump photons that spontaneously decay to two photons of complementary but random wavelengths. That's their energies add up to the pump photon. Another one is Raman scattering, where the pump interacts with the vibrational states of the two Kai2 material, and you generate peaks of noise photons near the pump. So when choosing the pump and the target, we need to make sure that the pump is first longer wavelength than the target, and that it is not too close to the target wavelength. So this tells us that converting from 493 to 1283 nanometers requires us to do it in 2 stages. And we conveniently choose the 780 nanometer to allow interfacing with neutral rubidium atom at 780 nanometers. Another consideration for us is that we need the QFC to be polarization preserving, because our polarization our photon is polarization entangled. And there are several different types of configuration that can provide polarization preservation using a single crystal. There's a double pass, Mach-Zehnder, and the Sagnac. In our case, we went with the Sagnac. It is inherently phase stable, but all of these 3 type of configurations to convert both polarization require high pump power. So what is the Sagnac? So the Sagnac interferometer setup is where you have an input and the output colors come in this same exact loop up until a beam splitter. So if you follow the 780 input here, it is incident on the beam splitter, and the H polarization portion transmits while the V reflects. And there is a half wave plate that is set at that's set to rotate the polarization 90 degrees right after one of the paths, in this case the H path. And so that H is turned into V polarization, which is the preferred polarization for the piplin, because again it's matched to one of the piplin coefficients. And on the return trip, it remains a V polarization and reflects back on this PBS through and gets transmitted through this dichroic mirror that allows 1283, but does not transmit 780. Now, on the other side, we have 780 incident on the PBS, V polarization through the piplin. It is now 1283, but also V polarization here. And then it undergoes a rotation, a 90-degree rotation to H and recombines as H. So with that, what do you think will happen to the entangled state after one stage of this? Yes, so the answer is B, that the sort of the entanglement will be flipped. Because H that was entangled with 1 here becomes V, but it's still the one that's entangled with 1. Whereas V used to be entangled with 0, and now it's entangled with 1, so it was swapped. Now, because we're doing a 2-stage scheme, after 2 stages, it writes itself. So even without any, you could, in theory, just put a rotational sort of a wave plate at the output and convert it back. But even without that, after 2 stages, this flip will write itself. Okay, so here's some data about this 2-stage conversion scheme. The QFC1, which I showed as the first Sonyak configuration in panel A here, you'll see 2 curves, one for each direction through the crystal, one for H, quote, polarization, although it's not really H, it's V, but it is that direction. And then the other for the V polarization. And you see that the conversion efficiency peaks and then decays as expected from the theory, and also that they are within uncertainty of each other, meaning that imperfections of the piplin crystal are due to coupling into the piplin crystal and not due to any of the phase matching error of the piplin crystal itself. Likewise, for QFC2, we see the peak efficiency at around waveguide, only the waveguide efficiency around 50 to 60%. That corresponds to about 33% in each stage, fiber to fiber, because there are optic losses. There are so many mirrors in the Sonyak setup that, even with 98% reflective mirror, used to have 2% loss, and they add up. And so after 2 stages, we have about 10% overall transmission. That takes is a hit on our rate, our entanglement generation rate, which is the other metric we use to measure our how good our entanglement is. Because we attempt to generate entanglement 50,000 times, 48,000 times per second. But because of the losses at 1287 nanometers, there's only 15 hertz estimated entanglement rate. So the losses and the conversion efficiencies all factor into the rates. Now, the fidelity we measured, I factored in the 97% process fidelity through the 2-stage conversion setup, and incorporated that into the hit in fidelity from 84 at 780 adding one more stage to 80% at 1287. And so that is some of the data we work with. Here is looking ahead to something that can be done on a quantum network, hybrid networking with neutral atoms. So the goal, because our rates are so low, one of the ways you can increase them is to you add non-destructive state measurements as flags, so that it and have the light stored in vapor cells, where the light maps its polarization, entanglement with the polarization gets mapped onto a collective spin state of the vapor. And using a method known as EIT, using a method EIT, you can engineer to retrieve that photon on demand. So once you turn on a control beam, it ejects the photon with the entanglement back. So what that is good is that if you add a measurement flag here, every time you see a photon arrive at the at one of the cells, and then you tell the other cell to and then you tell the other ion system to to keep firing until, and this system to wait. And once the other flag is raised, they can both be released to the Bell state analyzer, so that you don't have as much so that you can time synchronize the interference events, and thus up your rates of ion photon entanglement between two ions. This could even work with atoms. So that's something for the future. And lastly, just to demonstrate that we have, something on the Marquee network here, we did use a two-stage conversion scheme, but that is not entirely polarization preserving, to do a proof of concept demonstration around 11 kilometers of fiber to the Discovery Lab and back. And here is a histogram of the photo arrival at the ion, which is before it went into the network. And after 11 kilometers, we see the same photon shape is preserved. However, we do notice that there's a 7 dB loss, which is greater than the expected fiber loss throughout the 11 kilometer. And we know it's due to some butt couple connections in the fiber, or splice connections in the fiber. And hopefully we can improve that for when we, make better splices, or use a different fiber when you actually send send single photons down the fiber Marquee network. So that's some experimental results of sending photons from a trapped ion quantum memory down a quantum network. Thank you.
Okay, I think this concludes our class. So is there anything else we should be, I guess we can just wrap up since we're out of time. Thank you everybody for participating. Is there anything else we need to do before we can sign off?
No, everybody's good to go. I would just like to remind everybody that we will have a survey link coming out sometime this week, so keep an eye out in your email. But other than that, everybody's free to go if you guys are ready to wrap it up.
Thank you so much for everybody.
Yeah, no
There is
problem.
a question in the Q&A asking if there's any resource for our slides. I think there's a recording that's gonna be uploaded to the website, right?
Yes, the recordings of all these seminars will be uploaded in February on our YouTube channel. But other than that, that's pretty much it, everybody. Thank you guys for coming.
Thanks for coming.